first speaker this morning is Karla Peña Ramírez. We'll talk about revisiting VVX open clusters.
Well, good morning, everybody. This work kind of I made a subtle change in the title because, well, you're going to see why. This has been a work done mainly together with André Nicolás and with Sebastián Ramírez, and also with one master student in the Universidad de Antofagasta. And hopefully soon we will be joined by Hilo at Universidad Católica de Chile and Simon Goodwin and Becky Arnold at Sheffield University from the theoretical point of view. So basically, the motivation of this work arrived from my own interests because lately the differentiation between transforming regions, solving clusters, associations, moving groups has been kind of diluted with the time. And also together, we have now kind of a fairly well sampled IMF in different star-forming regions. And most of them say that the IMF seems to be universal within a certain range of masses, and it gives a typical characteristic mass around 0.25, 0.3 solar masses. But obviously the extremes are not so well constrained, and for that you need to follow a recipe to create an IMF. And the recipe mainly uses 3 steps. The first one is to build your luminosity function, then to convert that to masses, and then to make a kind of back process to go from the present day mass function to the initial mass function. But all of these steps have a lot of caveats. As always, anything is so simple. So I'm just going to mention a little thing about 2 of these 3 steps that is going to be concerned to the project that I'm going to show you later on. So in performing the luminosity function, you need a clear sample of clean members. And you usually do that in star-forming regions, clusters or associations, but that will require that you really understand the process of cluster assembly, because otherwise you are going to do a poor sample of sources that are going to be then a huge impact in your IMF determination. And once you understand the process of cluster assembly, equilibration, and dissolution, you can kind of make the real IMF construction. You also have to deal with a lot of contamination, and the problem is still even worse if you have to take into account the extension of the regions. And also, if you add kinematical information, this is going to be refined. In the point 3, in dynamical evolution, you have to correct for star formation history and try to use all the system dynamics to try to get out from the present day mass function to the initial mass function. And you deal with things like mass aggregations that, for example, affects very, very much the low mass sources, in that when you have different movements in comparison with the higher mass sources and in different parts of the cluster. And you have even loss of low mass members. So you are not accounting the entire population for the mass function. In the case of clusters, and in particular of embedded clusters, you can have this kind of relations that relates, cluster mass and cluster radius, age and radius of the cluster. And it's kind of sample, but this expression is still large. You have gaps that we are not really still sure that they exist. And this kind of process of plots at the end trying to trace you the galactic structure. So you need a sample also of clusters that have well-determined parameters. And if you ever go to the cluster formation scenarios, now we are kind of dealing with three kind of scenarios: the subcluster merging, clusters that the other scenario says that clusters are just formed and they are not further dynamics inside the clusters, and also that they behave like single entities and they grow by means of gas expulsion. And I like to highlight the recent work of Mike Kuhn, that with a sample of very well-behaved, let's say, clusters using the Gaia data release 2, he basically, the 75% of his sample shows signatures of growth, of expansion. So also, if you have different types of clusters, you have different types of formation scenarios, and the high degree of the low degree of clustering can also tell you if there is something behind, what is the dominant process behind the formation of the cluster. And even the shape of the cluster can also give you some trace about it. So we have a lot of ingredients going on to try to just not to put out an area and count sources, but you have to take into account a lot of more of scenarios. And that can lead you to the dominant formation scenario for the cluster. And what about large scale searches? So basically, I'm going to give you 3 examples of very, very recent results about what is going on if you kind of zoom out in the formation and start forming regions and see what is going on there. So for example, the Vela OB2 case is remarkable. It's a cluster that was kind of exploring X-rays at the beginning of this century. And then you kind of make a zoom out, explore a wider area, and you see that there are a mixed population. And just in the last year, with the Gaia Layer 2 release, basically you kind of see the overlap of different subclustering, that the area of the region is so much larger than the previously thought, and the mass budget increases also a lot, and it's even connected with an iris Vela shell. In the case of low mass sources, the case is even more intriguing because it seems that there is a preferential density and differential location of high mass sources and low mass sources in this area. And this basically just enlarging a little bit the sample. In the case of Scorpio Centaurus OB2 case, it's kind of similar, but this region is a much, much larger. It's about 2,000 degrees square. Making an IMF in this area is quite a challenge because the area is so large. And we have even in the low mass end of this kind of in this area, we have free floating planets confirmed in this area. So it's even harder because there is a population that is really there, but they are so faint objects. Here is the last kind of map of the region. So you see this density map in which the subclustering is quite evident. So this is a year from Damiani last year. And basically now you can have to divide in families, the different subclusters identified. And also this has implication about the cluster population and the cluster dynamics inside the area. And the remarkable case of Orion, one of the most explored regions ever. We have also new results. We made this work led by Marina Konkel using Apogee data and Gaia Layer 2 data. And basically what we did was to combine the data from these two surveys and make a 6-dimensional view of the entire Orion, from Orion 1b to Orion 1, and to divide the regions depending on parallaxes, distances, and radial velocities. For example, you can see even that there are substructures in the way that the stars move in these different parts of the horizon. So there are a lot to work on in these areas when you kind of zoom out your view and try to combine different data from different surveys at the end. So this subcluster view leads you to a question that is kind of problematic in terms of the definition of the IMF, because the cluster parametric iteration is kind of misleading in the way that you are counting in an area that is not so well defined. So trying to focus on that, thanks to a visit of Andre Nicolas to the University of Antofagasta, we kind of joined forces and say, well, time to face the challenge using the VVV data. And here you can see, well, the map of the VVV and VVX survey, but also a recent catalog that was made by Beacon. Basically, they kind of merge of the open clusters and, well, different classes of open clusters that are in the literature. And, well, this is kind of a minefield to try to go in detail in the open cluster studies and try to study them with this perspective. And here's some of the results. Here is just Gaia DR2 data, and this makes the process using only positions, proper motions, parallaxes, and this covers the 2 times the nominal size of the cluster. Here you can see the result of kind of the spatial clustering. Each dot is scalable to the probability of being part of the cluster, and also the color. Here you have, for example, proper motion. Sorry about the very small labels. And you see, for example, only with Gaia, you have kind of a substructure even in that tiny space. What if we join this with VVV data? So, for example, this specific cluster is in one of the border of the tile. So, our first, but no, the things work even if you have cutted tiles, which is going to happen a lot in the data. So you kind of have the distribution of the sources, especially, and we made the process only using the 5 bands of the VVV, 5 colors, and the positions, always with the 2 times the nominal size of the cluster. Here is the color magnitude diagram. You can see to your left the combination of Gaia and VVV. You can see also kind of the sequence of the cluster when I show the confirmed members of the cluster in red, and purely near infrared VVV data to the right, and you can see kind of our result. The structure that you see to the right, to the left, sorry, is duplicated in the near infrared data. And with this, we kind of got about more than 600 candidate members with this process. You can have also, for example, clusters that are quite rounded and highly clustered, and you see the results with Gaia, in this case, in the left, and with VVV data to your right. And it's, well, you can see like the upper part of the near infrared data is reproduced by the structure that is found in purely Gaia data. In the case of different morphologies, for example, not so rounded clusters, you also have the identification of the cluster in the light Gaia data, sorry, in the left Gaia data and in the right VVV data. And for example, if you even increase, if you have a very large cluster and you increase the nominal size of the cluster, you also have the results here Gaia, and here VVV. So basically, these are kind of the results of some of the cluster that we have been exploring in the disk until now with VVV. But what about very difficult regions, like for example, the galactic center? And in fact, thanks to Andre, he gave us kind of a test cluster to work with, and you see that the spatial configuration doesn't seem too highly clustered. And you can see in the plot the confirmed members and the sequence that the authors consider as members, and you can have the result. It's not so good because we are in the galactic center, but still at least the part of the confirmed members is totally reproduced. This is kind of the thing that I wanted to show you today. Future plans, a lot of future plans. Unfortunately, thanks to Phil Lucas, he gave me yesterday the one chunk of the Virac2 data to try to implement it, but it's in the corner of one of the working samples that I'm working with. So, but still with Virac2 we will increase the dimensions and it will refine this even more. We can also look out of the near contour part of John moving groups, for example. That would be a nice project. For my massive fellows, this is totally ready to include the Zodiac color to try to look for massive stars. So it can be a kind of a characterization of the known John massive clusters, of even try to look out for new. This is not tested yet, but it's totally doable, and the tools are already ready and implemented. And we can even go further and see if the clustering is tracing with gas content, with restriction maps, and this kind of studies. So thank you so much.
Thank you, Karla. Some questions to Karla?
I just wanted to, I was a little bit still waking up when you were explaining the scientific things we're trying to look at. I mean, I got you trying to get at IMFs and environment and so on. You mentioned trying to look at different modes of cluster formation. So what are these, like a rapid mode and a slow mode? What are the difference?
Yeah, what I meant is, let me just go back to yeah, what I meant is that once we have kind of a well-sampled list of clusters, and we can not only to reproduce, to try to assess them, the IMF of each of them, but also we can study the cluster itself as an entity and try to link the degree of clustering and the shape of the subclustering to different scenarios of formation for clusters at the end. Yeah. So it can be interesting because it's not only for assessing the IMF in different environments or in different regions along the Milky Way, but also to trace back and see if we can link that with the different formation scenarios of the clusters.
Yeah, yeah. I definitely would, just from all the looking at all the pre-main sequence clusters. I mean, for example, looking at nucleids, 85% of them are pre-main sequence rather than old, and so many of them are just long and very elongated ribbons.
Exactly.
And you imagine it was a filament that formed the stars and not anything that was round. So
exactly.
Yeah.
Yeah.
So I had a question about how you select your samples from Vika, because he has 10,000 classes and a lot of them are not.
Yeah.
But the VVV clusters are good.
Yeah. No, sure. And what we did was basically from the Vika sample, only select the open, what they put OC, open cluster, no open cluster candidates. And then
no OCC.
no OCC.
That's good.
Yeah, no OCC. And inside the OCC, there are plenty of VVV clusters that are now ready to meet this afternoon with my colleagues and work with.
Thank you.
Next question.
Karla, nice talk. I saw that you used, in several of them, used primary sequential models. And then I guess the first of the cluster that you showed is a very compact one. It seems that you have a turn on it. I don't think it is this one. But anyway, my question is, for the whole sample, have you got some statistics on ages or evolutionary?
Yeah, we are first trying to focus in very nearby joint clusters, but the idea is to just increase the sample, including more ages and more distances. We haven't got the time yet to try to see a link between age and
the size.
Exactly. We are not just there, but it's doable, and we have to do it.
Okay.
Yeah.
Thank you.